Welcome to the course on advanced machining processes. Today I am going to discuss electron beam machining process, that is EBM process. The organization of this talk is as follows: introduction, elements of electron beam machining system, process parameters, process characteristics, applications of electron beam machining process, and then I will lastly discuss dimensional analysis of electron beam machining process. Introduction: electron beam machining. Electron beam machining can be classified in two categories. The first one, the cathode is heated to a high temperature and electrons escape out to the space around the cathode, because cathode is at a very high temperature. So those electrons are emitted. Now let us see how this first one, which I have just mentioned, is known as thermal type of electron beam machining process. The second category is non-thermal type of electron beam machining process. In this talk I am going to discuss only thermal type of electron beam machining process, where highly concentrated large amount of heat is generated. As a result of that, as we will see, the workpiece material is melted and evaporated. As mentioned earlier, the cathode is heated to a very high temperature. As a result of that, a stream of a large number of electrons emits from the cathode as an electron beam. Now this beam moves towards the workpiece, and once it moves towards the workpiece and hits the workpiece, then bombardment of electrons takes place in a localized area on the workpiece. The area on which this bombardment of electrons is taking place is very small in size, and this kinetic energy of the electrons which are hitting this workpiece converts into the heat, and this heat is so highly intense that it can melt and vaporize any material, and it leads to a very high temperature. One thing is to be noted here, that electrons are considered as more or less massless, but they still have some mass, and the velocity with which these electrons are hitting the workpiece is very close to the velocity of light. So their kinetic energy is substantial to increase the temperature of that small localized area of the workpiece to the extent that the workpiece material melts, and in most of the cases it vaporizes and the material is removed. In the case of non-thermal type of, so finally melting and vaporization of workpiece material is the mechanism of material removal. It is not metalling, it is melting. Now in case of non-thermal type of electron beam machining process, electron beam causes chemical reaction on the workpiece surface, and it removes material once it hits the workpiece material. So here the mechanism of material removal is very different from the thermal type of electron beam machining process. I am going to concentrate, as I mentioned earlier, only to the first type, that is the thermal type of electron beam machining process. Here are some salient features of the electron beam machining setup. As you can see, that here is a cathode grid. As I mentioned, that this is heated to a very high temperature and it emits a stream of the electrons, which is written here as electron beam. Then it is attracted towards the anode, and that is shown here by this particular shape, and then there is a valve through which the beam of the electron passes, and here is the optical viewing device through which you can see the beam of the electrons passing through, and then there is a magnetic lens, and with the help of magnetic lens you can concentrate this particular beam on the workpiece, and when you want to deflect the beam minor distance left side or right side, then there is a deflection coil which helps in deflecting to a very small distance so that you focus the beam at the desired point, and this can be done with the help of the deflection coil. And there is a workpiece table on which the workpiece is mounted, and you can move this workpiece table with the help of CNC machine to small distances in X as well as Y direction. Now whole of this operation of electron beam machining and production of electron beam is done in the vacuum. Very high vacuum is there, and that vacuum can be achieved with the help of the vacuum pump that you can see on the right side. And if you want to see the workpiece and location of the workpiece, whether it is very right with reference to the beam, then there is another viewport with the help of which you can see the location of the beam on the workpiece and the removal of the material from the workpiece. So this is a schematic diagram of electron beam machining setup. Some more details you can see in this particular figure. It is just a detailed drawing of the same thing which I have just mentioned to you through the schematic diagram. Now another point which you can see here is oil cooled cathode insulator, because temperature is very high. So to safeguard the various devices, you have the cooling of the system over there where cathode grade is there. So oil cooling can be used for that particular purpose. And for creating vacuum, again you have one more gun pumping port where you can create the vacuum. Then if you see further, then rest of the things I have already shown to you through the schematic diagram in the last slide. So this is the industrial electron beam machine which is there. Now very important is to understand the working principle of electron beam machining. In brief, I have already mentioned to you that the kinetic energy of the electron beam gets converted into the heat, and the intensity of the heat is very high, which results in the melting and vaporization of the workpiece. It can produce holes of different shapes by manipulating beam movement by CNC feature of the electron beam machining machine. Now here you can see you can manipulate the beam to a small distances in XY direction to create different kind of the holes. However, you can also move the workpiece table if there is a large hole to be made, just like if you want to do the trepanning operation where large movement of the workpiece is important, then what you can do, as I show you here, that suppose this is the workpiece and you want to make a large size hole which may be of few millimeter, then what you can do, that you move the table such that the beam is always hitting on the periphery from where you want to remove the whole of the material. This is a whole of the material that is to be removed. So what you can do, instead of cutting or melting and vaporizing all of this material, you can perform the trepanning operation. So when you perform the trepanning operation, the shaded portion will come out as solid piece. But normally electron beam machining is not used for a very thick workpieces. So for even thin workpieces, you can use this trepanning operation for making the larger sized holes rather than melting and vaporizing whole of the workpiece material. So this way CNC feature is very useful for creating different kind of the features on the workpiece surface. It works well with electrically conducting as well as electrically non-conducting materials, as we have already seen that electric discharge machining, electrochemical machining, these are the processes which are normally used for electrically, not normally, always used for electrically conducting materials, but this particular process can be used for both conducting, electrically conducting as well as electrically non-conducting. Now vacuum is required in machining chamber to have better efficiency of the system. Most of the EVM system are vacuum operated, means they are operated under the vacuum. However, certain systems have been built which can operate under non-vacuum machining chamber. Such systems are also available, but their efficiency is low and quality of the product is comparatively poor. Because what happens in non-vacuum machining system, that these electron beam, when they hit the air molecules in the chamber, they lose their energy to certain extent, and you don't get the hole of high accuracy, just like the one in case of, you can get like this. In the another case, this may not be that accurate as we can obtain in case of vacuum electron beam machining chamber. So although it is expensive, but for better accuracy and higher productivity, vacuum machining chamber are more preferred. Now beam size is very important, and it should be smaller than the size of the hole. As you can see here, suppose this is the size of the hole that you want, then definitely size of the beam should be slightly smaller than this, because the total material that is being removed is slightly larger than the size of the beam. Now ejection of molten workpiece material is very important, and vaporized baking material comes out at high pressure, it expels molten material. This is important to understand, because I have mentioned that it is not used for high depth, and most of the material is removed by melting and vaporization both. So now the question arises, when it is not through, how this molten material or the vaporized material is going to come out. So what happens really is that, suppose this is the workpiece where you are drilling the hole, and here is the support. Now when hole has been made, then whatever is the molten material or vaporized material, that will remain at the bottom. So for this to eject out, what happens, this table, not really table but supporting material, this is the table. So what happens, this material melts, vaporizes and throws out the molten material and vaporized material out of the hole. For this particular purpose, this, as you can see here, backing material is very important, and it is used so that molten and vaporized material comes out of the hole, and you can take out this workpiece and you will get through clean hole. Non-circular holes can be made with the help of electron beam machining system. What one can do, one can move electron beam by computer controlled machines along the whole perimeter. Suppose instead of this circular hole, you want rectangular hole. So two ways are there, as I have mentioned earlier, that you can move the electron beam along this periphery. Then the material will be cut and you will get the non-circular hole, or you can move the table in X direction and Y direction in such a way that the beam is always along the periphery that is to be cut. So you can cut this. Now the two things are there. If the size of this is much larger than the size of the beam, then definitely you have to do the trepanning operation rather than the melting and vaporization of whole of this material. Otherwise it is going to be very inefficient and time consuming unnecessarily. So that point of view, the CNC feature helps a lot in getting the desired workpiece, desired feature on the workpiece material. The mechanism of material removal is definitely melting and vaporization of the workpiece material, as I have already mentioned. EBM can produce holes of different shapes using CNC machine, as I have explained over there. It works very well on electrically conducting as well as electrically non-conducting material, which I have mentioned in the earlier slide. But there are certain constraints as long as workpiece material is concerned, which I will show you later on. Vacuum required in machine chamber, non-vacuum chambers are also available in the market with lower efficiency. This is to be noted that the efficiency and productivity of non-vacuum machining chambers is lower compared to vacuum machining chambers. However, the vacuum machining chambers are more expensive. So I have already explained here that ejection of the molten workpiece material from the bottom of the cavity is important, and this is done with the help of the backing material. Now this is applicable for both circular as well as non-circular holes. Now vaporized baking material comes out at high pressure. It expels molten material from the cavity. Now let us see what are the various elements of electron beam machining system. First one is the electron beam machining gun. Second is the power supply to the electron beam machining system, and third is the vacuum system and machining chamber. Now electron beam machining gun, the operation is done in pulsed mode. It produces and focuses electrons beam at predetermined location. This predetermined location is made with the help of the lenses, etc. Now cathode is superheated, as I have mentioned with the help of the diagram also. An electrons cloud is created around the cathode, and this electron cloud is repelled from the cathode. It is attracted towards the anode because they are having reverse polarity, and magnetic lines converges the beam at pinpoint location. Now stray electrons are removed on the way and reduced diameter of the beam is obtained. As long as power supply is concerned, generators give the voltage, or you require the voltage approximately 150 kilovolt, and the power that is given to the system is around 12 kilowatt, and pulse energy is around 120 joules per pulse. Now please note that these values may be very different depending upon the system you buy and the objective for which you want to purchase this particular system. Invariably all systems have computer control of the process variables. There are various process variables which I will explain you in the following slides. Now mechanism of material removal is melting and vaporization. Final material removal is mainly by vaporization process. Now beam generation and travel is in vacuum if it is a vacuum system, or if it is non-vacuum then definitely in the non-vacuum machining chamber. Now no oxidation of filament takes place because it is a vacuum, so there is no oxygen, no air in the beam generation chamber or machining chamber, hence there is no oxidation of the filament, and filament has high life. There is no collision of electrons with air molecules because vacuum is there, and vacuum value is very high. It may be 10 raised to power minus 4 to 10 raised to power minus 5 torr. So these are some of the main elements of the EBM system. Now let us discuss the process parameters of electron beam machining process. Now process parameters, you can see there are beam current, pulse duration, lens current and beam deflecting signals. Now beam current normally varies from 100 microampere to 1 ampere. It governs energy per pulse, and higher value of the beam current will lead to higher material removal rate. But please note it carefully that not necessary that higher material removal rate will retain the same accuracy of the machine components. So one has to find the trade-off that between the MRR and the accuracy both. Now pulse duration normally varies between 50 microsecond to 10 millisecond depending upon the requirement. Smaller the pulse, better is the accuracy, but lower is the material removal rate normally. Now long duration gives you wider and deeper hole cavity, deeper hole or deeper cavity. It affects the heat affected zone and recast layer. I have already discussed at many places heat affected zone in recast layer. I am not going to repeat it, and the size of the recast layer is normally around 25 micron or less. Lens current determines the working distance and the beam size, because beam size is going to be governed by the lens current to some extent. Then beam deflecting signal, hole shape, as I mentioned that you can deflect the beam and get the different type of the hole rather than only the circular hole. So you can utilize this feature that position of focal point below top surface of the workpiece is there. This is important point that you have to check that the focal point is not far away from the surface which is being machined, because if focal point is far away then you will not get the proper machining efficiency. Just let us take the example. Suppose this is the workpiece being removed and you want to remove the material from the here, and your focal point is beam focal point is here, then definitely it is not going to give the total or maximum heat that should be given to the workpiece surface. Part of the heat will be given because your focal point is away from the workpiece surface. So this focal point should always be here. Or suppose you have machined a hole like this and you want to machine it, then this focal point should be shifted over here, then only you will get the maximum efficiency of the system, otherwise not. Shape other than circular can be obtained, as I have explained, with the help of the movement of the beam or with the help of the movement of the workpiece table. Now for calculation purposes we need to calculate theoretically what is the material removal rate and what is the specific heat requirement, so that a unit amount of material can be melted and vaporized from the workpiece. Material removal rate is normally given by zeta P over W, where zeta is cutting efficiency. Now it is a very high value written over here, 20% seems to be higher. P is the power in joules per second and W is the specific energy in joules per cubic centimeter. If you want to calculate the specific heat required to melt and vaporize the workpiece material, then this is given by W is equal to CPS multiplied by Tm minus Ti plus CPL multiplied by Tv minus Tm plus HF plus HV. Now here CPS is the specific heat of solid. So what you are doing really, that you are melting the solid up to the melting point, because Tm is the melting point, Ti is the initial temperature or the room temperature or the vacuum chamber temperature, and CPS is the specific heat of solid. Same way you have the CPL, that is the specific heat of liquid over here, and this is the boiling point of the material, and Tm, as we know, the melting point of the workpiece material. So that will give you the specific heat of the liquid, and then you need latent heat of fusion and then latent heat of vaporization. So this way you can calculate the specific heat requirement for melting and vaporization of unit amount of workpiece material. And this is very essential when we want to theoretically calculate the machining efficiency of the system, because whatever amount of material is being removed, if you know what is the amount of the heat required for that and what amount of heat you have given to the system, then the ratio of these two will give you the machining efficiency of the EVM system. And this is normally low, as I have mentioned in the earlier slide, 20% or less than 20%. Now let us see how the surface roughness is being affected by the pulse energy. I have mentioned earlier also that you have to normally make the trade-off between the material removal rate and the accuracy that you are going to obtain. Similar thing is true for surface roughness. As you can see here, that as the pulse energy is increasing, the surface roughness value, that is the RA value or RZ value, is increasing for two different type of materials. That means smaller the pulse energy, better is the surface, smaller is the pulse energy, better is the accuracy, which is very simple. I will explain you that if pulse energy is small, then your size of the beam is also going to be small in case of low pulse energy and in case of large pulse energy. Definitely it is going to give smaller or better accuracy as compared to this. However, this can also have a smaller diameter, but then because of high energy intensity, the melting of the material surrounding this will be larger compared to this, and you can have or you will have poor accuracy in case of larger diameter compared to smaller diameter, or larger pulse energy compared to smaller pulse energy. But material removal rate is going to be low, so it is going to take longer time. Now here you are given, suppose you are given a workpiece material. Now if you see that as the thickness of the workpiece material is increasing, this is the diameter to be drilled and this is the drilling time. Process characteristic. Now let us discuss the characteristics of the electron beam machining process. It is applicable for electrically conductive as well as electrically non-conductive materials. At entry side of the beam, a small side burr is normally seen. Workpiece properties do not affect performance of EVM process to a large extent, because the amount of the heat that is produced or intensity of the heat that is produced on the workpiece surface is very large. So it really does not matter too much what are the properties, thermal properties of the workpiece material. To some extent yes, it affects, but not to a large extent. A small diameter hole can be made as small as 0.1 millimeter and large size 1.4 millimeter. This will definitely depend upon various factors like the pulse energy and size of the hole that you are obtaining, size of the beam that you are obtaining after concentrating the beam. Aspect ratio is not greater than 15:1 in most of the cases unless special arrangements are made. Now as we have seen in the mechanism of material removal, the process is purely thermal process where material is being removed by melting and vaporization, so no mechanical forces are acting. As a result of that, fragile, thin, low strength component can be easily cut or machined, or different shapes can be created on these components, which is not possible in case of mechanical processes. Off axis holes also can be easily made because there is no mechanical type of the tool, so it is not necessary that always you are making the holes along the axis. Off axis holes can also be made by deflecting the beam. Residual thermal stresses are produced on the workpiece due to high temperature gradient. This is very important because this is a thermal process. Material is being removed by melting and vaporization, and there is always very high temperature gradient, and because of this you are always left the machine component with thermal residual stresses, and in many cases you require to anneal such kind of the pieces or remove those thermal residual stresses before putting them into the devices. Very high investment cost, and it requires skilled operators. Machined edge quality is the function of thermal properties of the workpiece material and pulse energy, and heat affected zone is the function of pulse duration as well as size of the hole being machined, and hole diameter is not constant along its length. Although we expect that the diameter of the hole should be constant, the walls of the hole should not be tapered, but normally it is not the case. As you can see here, that this is the schematic diagram of a hole that has been machined with the help of the electron beam machining process, and the size of the hole at the bottom is just 125 micron, while size of the hole at the top is larger than this particular one, although value is not written there, and the depth of the hole is 400 micron, and you can see the diameter is slightly varying from top to the bottom. So you are not getting the hole of the same size throughout, and this you can see here, this is the cavity of the hole, and this is the diameter of damaged layer. As I have mentioned earlier, here the recast layer is not shown, but you can clearly see the kind of the heat affected zone or the zone which has been affected due to the high temperature gradient. So this is the area which has been affected by the very high temperature gradient. The cross section of cavity made by a single electron beam pulse in chromium molybdenum steel. Now this is a deeper hole but a smaller size, and again you can see this is not of a constant diameter throughout, the diameter is varying along its length. Now here again this is the heat affected zone, and this is the hole diameter, and again some heat affected zone, and this is the cross section of the hole that has been drilled, and the you can see the scale is given over there, so one can find out what is the depth of the hole and what is the diameter of the hole and what is the size of the heat affected zone. Now applications are very important for this particular process also as for any other manufacturing process. This particular process is very popular in aerospace industries, insulation, food and chemical industries, clothing industries, etc. Hundreds to thousands of holes in a workpiece may be required many times, and these holes, not just a circular hole, many times you need complex shaped, difficult to machine materials, perforations, etc. in the workpiece you may require, and to make such small micro holes in difficult to machine material is really difficult. Example, turbine engine combustor mode. I will show you the figure of this. Fiber spinning head, thickness less than 5 millimeter, much faster than EDM process to make hundreds of holes over there. Holes in filters and screens, especially used in food industry and textile industries. Fine gas orifice in space nuclear reactor. Holes in wire drawing dies, because there are wire drawing dies which can draw the wire of less than 0.5 millimeter diameter or so, and in such cases to make first the initial hole in the dies with the help of electron beam machining, then you can draw the wire with the through that particular hole in the die. And cooling holes in turbine blades and metering holes in injector nozzles. This is the injector nozzles, not injector nozzles. Now let us go further with regards to the applications of this particular process. Now you see here here is a part of the workpiece where holes have been drilled, and you can see on the right side the hole diameter is, this is wrong, please correct, this is 0.9, this is really 9 micrometer, and the hole density is here, 4000 holes per square centimeter, and the workpiece is made of stainless steel, and the thickness of the sheet in which these holes have been made is made as 0.2 millimeter, that is 200 micron size, and the time taken per hole is just 10 microsecond per hole. Now people are not satisfied with this quality and this size of the hole, especially textile and food industry. They say no, we want still smaller holes, and here you can see in the next slide at the bottom the size of the hole is just 6 microns, and here the density of the hole is 200,000, this is again some mistake, 200,000 holes per centimeter square. Workpiece is stainless steel and the thickness of the sheet is 12 micron, and the time taken per hole is 2 microseconds. Now you can see such a high density of the holes and such a small time for drilling a hole, you cannot do it by other processes. There are some other applications which you can see here, that vector scan writing method, and this is each dot has address output from a computer through a DA converter, data digital to analog converter, to a beam deflection and blanking system kind of the thing. Then one spot 2.5 micron by 2.5 micron, as you can see here, that has been created with the help of EVM process. And in the case of C and D, deflecting beam on the chip, they have make certain circuits kind of the thing of 6 by 6 millimeter, as you can see over here. Now I am going to discuss, with this brief introduction of electron beam machining system, dimensional analysis of electron beam machining process. As we have seen, the filament heat raises the emitter temperature to a large value. It emits electrons that flows, and electron current is considered as I. Electrons are accelerated by a voltage V0, hence the power of the electron beam becomes I multiplied by V0. By collimation and focusing devices that we have already seen while discussing the EVM system, the beam diameter is reduced to the D, and this electron beam impinges on the workpiece wherever you want the feature to be created. Now the workpiece velocity relative to the beam is taken as V, and penetration depth is taken as I. Then dimensional analysis for developing functional relationship between the different parameters and penetration depth, we proceed as follows. This is the penetration depth L, that becomes the function of power, relative velocity between beam and workpiece, diameter of the beam, this is thermal properties of the workpiece material, density of the workpiece material, and temperature of the workpiece material wherever that beam is concentrated. Theta m is the equivalent temperature to which the workpiece would have to be raised. In rho c, theta m is the total energy per unit volume required for melting. It includes heat required for phase changes, that is the latent heat for fusion as well as latent heat for vaporization, which I have shown to you the equation in the earlier slide. Now this table gives you the name of the variables that we are going to use. Units of the variable and dimensions of the variable. Penetration is millimeter, L is the dimension. Power is millimeter kg per second, and m L raised to power 2 T raised to power minus 3 is the dimension. Velocity v millimeter per second, L T raised to power minus 1, diameter millimeter L. Its specific heat is millimeter kg per second per degree centigrade. This is per second per degree centigrade. So minus 3, second raised to power minus 3, and as you can see here, ml T raised to power minus 3 theta raised to power minus 1. Rho c kg per millimeter per degree centigrade, and T raised to power minus 2, T raised to power minus 2, which you can see here in the units also. And theta m is the equivalent temperature, that is theta and degree centigrade. Using this table, now we will perform the dimensional analysis. Now one thing you can see here, there are 7 variables as listed over here and 4 dimensions, L, M, T and theta. So you can have 3 dimensionless variables and they can be evaluated later on. Now using the pi theorem, you can develop these equations which I am going to show you. So let pi 1 be the dimensionless parameter, and let it be given like p raised to power alpha 1, k raised to power beta 1, rho c raised to power delta 1 and v raised to power phi 1 multiplied by L. L has the unit power. So now what you can do, you substitute the dimensions like for p m L square T raised to power minus 3 whole raised to power alpha 1, for k m L T raised to power minus 3 theta raised to power minus 1 beta 1, and then rho c m L minus 1 T raised to power minus 2 theta raised to power minus 1 delta 1, L T, that is the velocity, L T raised to power minus T raised to power minus 1 phi 1, and L, that has the unit dimension. Now similarly you can have second dimensionless parameter, that is pi 2. Same procedure is followed here, p raised to power alpha 2, k raised to power beta 2, rho c raised to power delta 2, v raised to power phi 2 and d. Now you can see the difference here, d is used, that is the diameter, here L is used alone with unit power, and then again substitute the values of the dimensions like m L raised to power 2 T raised to power minus 3 whole raised to power alpha 2 and so on. Then there is third parameter, rather variable, dimensionless variable, pi 3 p raised to power alpha 3 k raised to power beta 3 rho c raised to power delta 3 v raised to power phi 3 theta. So again substitute the values of the dimensions, and you can see again here theta is having single power. Now this way you will obtain 3 different equations. Now these equations, solve above equations to get 3 dimensionless variables, solving for pi 1 from equation 1, combine the exponents of each dimension on right hand side and then equate with the dimension on the right hand side. What you see, you find out the dimensions of each MLT theta on the left side, MLT theta on the right side, and then exponents can be equated on both sides as done here. You get this equation, m raised to power alpha 1 plus beta 1 plus delta 1 L raised to power 2 alpha 1 plus beta 1 minus delta 1 plus theta 1 plus 1 T raised to power minus 3 alpha 1 minus 3 beta 1 minus 2 delta 1 minus theta 1 and theta raised to power beta 1 minus beta 1 minus delta 1 is equal to m raised to power 0, L raised to power 0, T raised to power 0 and theta raised to power 0. From the above equation one gets alpha 1 plus beta 1 plus delta 1 is equal to 0, because you equate this particular power to this particular power, this particular power to this power, and this power to this 0, and again this power to this. So what you will do, you will have 4 different equations and there are 4 different variables, so you can find out the value of each variable. Then second equation, 2 alpha 1 plus beta 1 minus delta 1 plus phi 1 plus 1 is equal to 0. 3 alpha 1 minus 3 alpha 1 minus 3 beta 1 minus 2 delta 1 minus phi 1 is equal to 0, and minus beta 1 minus delta 1 is equal to 0. Solve these 4 equations for 4 variables, you get the values as follows. Alpha 1 is equal to 0, beta 1 is equal to minus 1, delta 1 is equal to plus 1, and phi 1 is equal to 1. Now following the same procedure, before that you get, now what you get the value of, you substitute this value of alpha 1, beta 1, delta 1 and phi 1 in the first equation that I showed you in the earlier slide. So you get pi 1 is equal to rho c v L divided by k, as you can see, it's substituting these particular values. Similarly, what you can do, you can follow exactly the same procedure for solving for pi 2. Again you will have 4 equations, 4 variables, evaluate the values of all the 4 variables, that is alpha 2, beta 2, delta 2, phi 2. Substitute these values in the second equation in the earlier slide, and you will get pi 2 is equal to rho c v d over k. Same way for the third, pi 3, you will get k square theta divided by p rho c v. Now using these 3 equations, what you can do, assuming that pi 1 is a function of pi 2 and pi 3, then you will get this particular equation. Here this symbol is the function, and this is the pi 1, this whole of this is the pi 1, this is pi 2, and this is pi 3. So you get this as a function. Now the question arises how to evaluate this particular function, because we do not know, theoretically at least, what is this function going to be. So what researchers have done it, that they conducted the experiments and then plotted the relationship between these and then found the solution for it. Now we know that this linearly affects, this particular pi 1 is affected by this particular, that is pi 3, and it is linear because this length or depth of penetration is a direct function of the power p. We know this experimentally as well as theoretically also, that depth of penetration should be direct function of power p. So what we can do, we can take the single power of this, and definitely this is power is going to directly affect this parameter. So this is reversing, that means p rho c v becomes in the numerator, k square theta becomes in the denominator. That means we are still left with what is the relationship between the depth of this particular rho c v L over k and rho c v d over k, that has to be evaluated. So what they have done, they have plotted the relationship between theta L k over p and v d over alpha, and based on experimental data of electron beam machine welding, they have found that L k theta over p is equal to c v d over alpha raised to power minus 1 by 2, where alpha is equal to k over rho c thermal diffusion, c is equal to 1. So this way they are able to find out the slope of this particular curve, and finally they are able to find out what is the actual relationship in these pi 1, pi 2 and pi 3, and from there you can find, with the help of dimensional analysis, the value of L, that is the depth of penetration, in terms of controllable variables. Thank you very much.